first of all, let's introduce Rust. Rust has system-level control and high-level abstraction, and many blockchains already, Yeah, is it better? Oh, great. Many blockchains already adopt Rust. For example, Solana, Polkadot, and Near, because of its performance and safety. Rust has compile time guarantees to reduce runtime bugs, which is critical for the smart contracts. Rust has ownership model, which means that every value has only single owner, and ownership could be transferred, but old owner is prevented from the usage. Because absence of the garbage collector, memory is freed deterministically when owner goes out of scope. This is an example. We have a value x with a string hello. We transfer ownership to y. We could print y, but x is no longer owner of the string hello. Rust also has borrowing and references. Borrowing could be done in two ways, immutable and mutable borrowing. Compiler enforces no dangling references, and compile time checks ensures that references don't auto the live data itself. In smart contracts, this prevents reentrancy by controlling the access to the mutable state. Lifetimes in Rust annotates how long references are valid, avoiding dangling references. In this example from the function longest, we can see a lifetime of a for every input and return value, and we could be sure that reference of the return value can be greater than input lifetimes. In contracts, this ensures that state references remain valid during execution. Sorry. At the compile time, we also have overflow and underflow checks. Rust defaults to checked arithmetics, integer, overflow, underflow, panics at compile time. In contracts, these checks prevents malicious large inputs to corrupt smart contract data. Memory safety in Rust is really important. Rust enforces no null pointers or dangling pointers. Ownership and borrowing mechanisms ensure safe memory access without runtime. Overhead, we also have type option that replaces null pointers, which can help avoid vulnerabilities to the exploits. Rust is used for the smart contracts of Solana. They are called programs, and they are written in Rust. Anchor is a Rust framework for developing Solana programs. It's a practically set of macros to reduce boilerplate. Anchor also uses Rust type system to define account structure. This is the example of one Solana program written in Rust. Name is hello. We have one function to init, and we have accounts for the context for the init function. We can see that we have lifetimes, mutable borrowing result as a return type, and for example, no semicolon for the return value. Substrate in and ink. On Polkadot, parachains are made with pallets. Pallets are written in substrate, and ink is Rust-based DSL to be executed on Polkadot. It uses Rust macros to reduce boilerplate, macros like ink message for functions, ink storage for storage, of course. It also inherits ownership, borrowing, and memory safety. Ink contracts are compiled to WebAssembly and can be executed on parachains that implements contract palette. This is an example of the simple flipper contract written in ink. We have macros for ink contract, constructor message. We also have mutual borrowing for the flip and regular mutual borrowing for the get. Next is Noir. Noir is Rust-inspired DSL for writing circuits in zero-knowledge proofs. It's developed by Aztec. It uses compile times check to enforce circuit constraints. We have simplified borrowing model. References exist, but lifetimes are static. So there is no borrow checker. This is the example of the one function and implementation for the NOR contract. We have assert, we have mutable references, generics, etc. Next is move. Move is smart contract language designed for the many blockchains, but currently is adopted by SUI and Aptos. Move is resource-oriented language, and it's designed to ensure that assets cannot be destroyed or copied. Sorry. It uses generics in models and functions. One model is practically one smart contract for SUI or Aptos network. Compile time safety is guaranteed because verifier enforces no double spending, time safety, and memory safety. This is the example of the counter contract written in Move. We have object counter with a key, ID, owner, value. We could create, increment, set value. We can see that syntax really resembles Rust. We have mutable borrowing, assert macro for checks. Lifetimes in smart contract development, in Rust-based smart contract development, are really important because that they ensure reference don't outlive the data and there is no dangling pointers. In Ink and Anchor, lifetimes annotate only context data to ensure safe borrowing. NOR does not have lifetimes, as we mentioned, because every value is copied and all the references are static. Move handles lifetime implicitly because every object is live until we destroy it or move it. Next are compile time checks in smart contract. Rust provides overflow and underflow checks to prevent integer wraparound exploits. We also have ownership and borrowing, as mentioned, because we don't want to have nulls or dangling pointers. Type safety is really important because we can write functions that are compatible with any type. We don't have garbage collector, but we have deterministic execution, which is essential for the blockchain. How to handle errors in Rust-based smart contracts. We have a type result that is used for error propagation. We have error of type E, and result of type T. Ink and Anchor uses similar result type, and Ink and Anchor contracts are reverting on result error. NOR uses assert to enforce proof conditions, and Move uses assert macro to abort transactional failures. How to prevent reentrancy via borrowing. Reentrancy is a famous attack vector in smart contracts. It arises when contract makes external calls which then call back the contract and try to mutate the state unexpectedly. Rust have mutable borrow, which is enforced to be only one mutable borrow references at a time, which prevents reentrant state mutation. Generics in smart contracts. Ink supports generics for storage. Move uses generics like in this example for the ID function, which demonstrates polymorphism, allowing function to operate with any type T. For example, we could send uint or string to this function, and it will always return the same type as we send it. Anchor uses generics for CPI accounts and contexts, and generic codes compiles down to the without runtime costs. Because we have, for example, this function ID in after compilation, compiler would enforce one version, for example, of function ID with you int one version of ID with string and paste it with no runtime costs. Well, last but not least, what are the best practices for the Rust-based smart contract? We should always prefer immutability if it's possible. It's better to use let than let mute if we don't want to mutate state. Be aware that we need to be careful when writing unsafe code. We need to be good in testing and try to minimize vulnerabilities. And we need to always use unchecked arithmetics to avoid overflows and underflows. We could use checked add, checked mul, etc. That's it. Thank you.